How's it going, everyone? Euler Gonzalez here again, looking now at the Redux fundamentals. And this is now how can we create. So first, what is a problem that Redux solves? And second, how can we actually write these solutions? And then dive deep into this topic as a way to now understand what is the value propositions of this particularly tool called Redux RTKey, which is, after all, is a middleware around Redux, and Redux is this well-battle test state management. So what is this state management? Is because the way how now we create user interface or applications, whether it is on the front end or the back end, we need to find a way to make the state predictable anytime we mutate them. So as a way for us to now have the ability to know what's going on when we update the value of certain property, or when we mutate the state of our applications, Redux actually has inspired on Flux architecture. So this is one of the design goals and intent that is designed, that is designed to make state management or state mutations predictable by using the Flux architecture, which is a way of how now you can update an state, is a way of how you can build this state management mechanism. All right. So when you have now your action that is going to dispatch that based on the action that you are going to want to mutate the state, and therefore those state now will be reflected on the UI, on all of the functions that wants to subscribe to this state as a way to see what's going on. So this is something interesting and beautiful because with that, all right, today's video is about how we're gonna see how Redux actually works when you're writing middlewares, and then some of the advanced things, especially how you can now hook up with hooking up with React as a way to understand how that thing works, because at the end of the day, that's exactly what is the value that we're going to provide. And also how you can connect Redux to React, right? How you can now hook up React, how you can hook up, let's say, how you can hook up with React, okay? And now connecting Redux to Redux or to React, right? So this is a subtle difference here, and the idea here is to understand now how these particular tools, when you actually integrate with React and Redux, actually works behind the scenes. So you will know, we're gonna talk about that and what is the value proposition of Eimer and that kind of thing. So again, in today's video, we're gonna take a look now at the middlewares and then how we can hook up with React, right? And that's why we're starting to describe is what is the, at least based on this, from one of the maintainer of Redux, the Mark, the intent and design of Redux is to now actually understand now what is the goals and intent, which is, as I mentioned before, is to make the state mutations predictable using the Flux architecture, which is the way of how you can now build this particular way of how you can make that happen. And it also, because we want us to know what happened, we want to have a log, we want to have now improve the developer experience. That's why we need some sort of constraint, for example, like immutability and serializability, okay? And also, when you want to update your state, all of those state update must be synchronous. And if you have any asynchronous behavior, some sort of side effects, so you're calling a function and you have to wait for that function, or you have to wait for that value, and yeah, you have to wait for that value until completion. That's why we separate is the asynchronous behavior from the act of updating the state. So that's when we have now middlewares and also things like Thunks. What are Thunks? Which is a time-independent wrapper around a value, which is a fancy word to say, hey, this is now. I don't care when this data is available. I just want to get me that. Okay. And when you're going to design is your states, it is important to, instead of actually having multiple states, you're gonna combine all of them into one state, so you can now cover some main use case. So for example, you want to persist the state of your applications. So for example, if the user now close this tab, you want to persist now the state of the application once he reopen that tab or open a new tab in with your website. Also, in the case of the server, it's like, hey, I want you to now preserve this particular state in memory, in cache here, or in main memory, anytime a user now is requesting this kind of data, right? So, and for that, well, we have now this global store, which this global store not only make it possible to do this, but also to make the code much more easy to test and to maintain, as well as to understand the data flow of this. And not to mention that because we want us to now combine all of this update logic, aka reducers, well, at the end of the day, yeah, at the end of the day, we want is to now have a single point of have a single entry point or root reducer, root update logic maintainer, where we're going to add all of this logic, where we are going to put now what are the particularly, or how we're going to handle the data in there, how we're going to handle the data to mutate that. So that's quite interesting, because this particular influence in gold, if we're able to describe that, followed by the designs, okay, what are the Redux maintainer have in mind, right? Which is, we take inspiration from Flux architecture. And also, we're gonna make our state management, state updates maintainable as a top priority. Thanks for that. And also, the action history must be semantic. Must be semantic. So all of these actions that you're going to dispatch to update the state, it makes a lot of sense. Not to mention that once we are doing this update logic and all of the things that I mentioned, we need to use some of the functional programming concepts as a way to make that happen, as a way to make the state mutations maintainable as a top priority. So we started to see now and describe why we are using this particular tools, this abstract tool, the functional programming, as a way to make the state mutations predictable. So far, so good, right? Now, we also looked at the idea is to make the Redux store minimal as much as possible, the API minimal as much as possible, and minimal and minimal and extensible, right? When we have now the ability to understand the data flow easily, So the update logic and the data flow are explicit. So all of the things is what exactly we're slowly doing this over the couple videos by understanding now Redux in theory and also in practice in all of the API that Redux allow or provide for us. So for example, create a store. So as a way to now make this state mutations maintainable, it provides now us this object, which is the create store. That is a just plain JavaScript object that contain is just JavaScript functions. So on that, right? The idea is okay. So the idea, on that, the idea is that once we're able to look at what is create store actually doing behind the scenes, and also a particular function called compose, which is a nice little function. This is what this create store actually provide to you. Once you call that, it has now this particular object with functions attached to. Okay, so Redux, especially when we are now using is create the React API's compose functions, is just a way of how you can now is given by calling several functions. So giving the output of the first functions will be now the argument of the second one, and so on and so on and so forth until you get now the final output, the final shape of the data that you need to, right? This is quite interesting because as we look now at how can we create our reducers, these update logics, and how we create our actions. Again, all of this is following is the Flux architecture. And then when it comes to combine them, because anytime you define an actions, you have to follow a particularly Flux actions notation or convention. And actually doing that over and over and over and over can be lead to some error prone at some point. You can misspell that, which is something that we did, for example, here. And that's why instead of actually creating this single objects, we create now a functions that is going to generate that for us. All right. So this function is now much more easy to test that actually do what it's supposed to do, which is returning the proper type that we're passing to as like this. Okay. And because in React, in Redux, right, we want is to now make that state up. We want is to dispatch an actions in any time a given actions we want. So instead of actually call out a store that has this particular property called dispatch, and they now pass the proper actions to update the states, Redux say, hey, let's go to actually make this straightforward by providing you this bind actions methods, bind actions creator, which is what it is. Don't you have that? I don't believe it. Anyway, let's go to the example. This actions creator is here, the dispatch. So instead of us having to, no, this is intro to Redux, exactly. So instead of us having to actually is call the store and then dispatch and then the actions every single time, right? So they say, hey, let's go to create now a function that actually is sure that. So by passing is all of these actions creators behind the scenes, what we're gonna do is to not only map each one of those actions that we're actions creator, actions functions, but it also is for each one of those elements, we're gonna call compose with is now calling is the dispatch. Is this calling this actions creator, all right? Which now is going to return the proper actions to the store.dispatch, which is exactly what it's doing here, right? This is the thing that we can assume that it's doing behind the scenes, right? And this particular function that we're passing is actually doing something else. It's adding some logic to this as a way to now we receive is this dispatch actions, right? Or this particular actions like this dispatch increment and dispatch add. So all of this is great, interesting, and by looking now at another API, which is the Redux compose. Reducer compose. Okay, we also look at the subscriber, which is just putting a function that any time we want to get access to, or any time that the state updates, we can listen for new updates. All right, and when it comes to look at another API, which is, and put it here, the Redux, that's right, which is API here, right? The combined reducer is that because we can have multiple update logics, all right, that is going to now update a particular state. So instead of actually having one giant reducer that is going to update all of the state, which can be quite hard to maintain and error prone, that's going to now split that, abstract that, create that into a particular model where these reducers are going to now handle the update logic per state. So far so good. And then we also have another one that is going to manage that, and so on and so forth. And then we want to now combine all of this into a single root reducer, which is exactly what it's doing behind the scenes. We also look at that particular example, the combined reducer, and how we can pass now the initial state into our reducer as a way to now make it much more easy to test these functions. So good. Again, so far we have looked is now at the compose, the create store, the bind actions creator, and the combined reducer. Right now a word for the enhancer and the middlewares. So this particular concept here on the enhancers is that what it is this one. So the enhancers, after all, they are currying functions. Yeah? What is the F of this? Is a functional programming. They come from the functional programming concept. Remember, we're using all of these tools, or the developers are using all of these tools, because it makes the state mutations maintainable. Okay, so that's what we have now, currying. And the currying and partial application, both of them are specialized techniques that allow you to get now, once you call a function, you're gonna get now a specific output. And once you wrap that specific output and pass that to a new functions, you're gonna get that you're gonna get another specific output. In other words, so for example, if you want to go out and to take an ice cream with 3 flavors, okay, so it has to pass one, for example, tiramisu, banana split, and lemon. You shouldn't combine this, but in any case, you have your ice cream, okay, you're actually asking to put the ice cream, right? Please serve me that. So you go, the seller is say, okay, let me actually put the tiramisu here, right? So what it's doing is that this stage and where it's putting the ice cream, okay, it now going to be is the next phase for putting now the tiramisu. So it first put the banana split, and then he puts the tiramisu, and then he put the lemon. That's horrible. You shouldn't make this, but in any case, the idea here is that you do this one and then the another and then the another. This particular step, you do this, and then you get a final outcome, which is your ice cream. And that's exactly what currying functions are doing. That is that, hey, I'm gonna get this input and give you now a single output. That's what curry is doing. So another good example is that for a motorcycle assembly line, when you have first the design and then the materials and then starting to mount the frames and so on and so forth, you know. So one input is the input of one phase. One is transformed, create now an output that'll be the input of the next phase, and so on and so forth and so forth. The subtle difference is that with partial applications, we're gonna preset the arguments initially and then pass the rest along the way. Where now with currying functions, we don't pass anything initially, and we're gonna pass then arguments each at a time. So we're gonna get this now: single input, single output, single input, single output, single input, single output. And this is way much more management for a human perspective. That's very, very interesting. Very, very interesting as a way to understand that, bro. As a way to understand that. So both are specialization techniques. Partial application presets some arguments, now receive the rest on the next call, and current doesn't present any arguments and receive each argument at a time, right? So most of the time you're gonna see in libraries using is loosely currying or partial currying because it's the convenient way of how now this data is returned, is the shape of this data. Again, this is go beyond to the technical aspect, but the TLDR of all of this is to understand that this enhancers, this currying function is applying some transformations, okay, to get you now a specialized object, to get now a specialized output here. So these enhancers it is useful for adding or changing the global store, these JavaScript objects. And here enhancers are actually used for DevTools as a way to see when an action is triggered and how long it takes an action to trigger, or a reducer, this update logic, to be updated, so on and so forth, right? That's quite interesting. So because now we also look at that specific example here, like this, as a way to create our own functions, right? Basically is that. So as a way to create our own functionalities, right? In this case, this is a way to enhance now what we can do in our store, right? So enhancers are actually that. It allows you to now add or change functionality to your global store, which is a plain JavaScript object with a lot of function attached to it, with a couple function attached to it, where you can now use that for the development process. And this is what it's doing behind the scenes. So you can see is now currying, strict currying, and then you have now this partial application, right? where we're gonna define some sort of logic, okay, that the output or this transformation will be now the input for the next function, right? So we get now a specialized functions along the way. And the reason we're passing here enhancers, right, is perhaps for some memorization techniques. And I say that because is to check that functionality actually exists as a way to catch that functionality, right? And only runs once, because now this enhancers only runs when your store is set up, when you run your store, okay? So it is run when creating the store, which means have access to the entire process. And then we look now at middlewares. So middlewares here, which is a fancy way to say that this is a function that now intercepts something and then do something, right? So this middlewares intercept now are dispatchers, or yeah, exactly, it is intersect actions, which is allow you to now add behavior between dispatch and reducer, between the action that you dispatch and the update logic. So it changed together with apply middleware, which is, hey, I want you to now intercept is these actions, and I want to bind several of these intersections. So you can now it runs unlike enhancer that runs when you store the when you run this when you're creating the store, okay? Middlewares now are trigger is any time the dispatch function is called, right? So it acts between the dispatch and the reducer. So you can now not only run these particularly functions before the reducer and after the reducer. Why this is important? You might wonder. Remember that after all, reducers are just the way how we can now update the state. Okay, and this is one of the most popular things that you can use as a middleware is to now perform some async operations here in middlewares, right? So once you intersect now then this is also very beautiful for Redux saga and that kind of thing. So now that you intersect that particular, let's say, now that you intersect that particular actions, okay, before updating that state, you want is to perform some sort of side effects, right? API AJAX request or HTTP or fetch HTTP, right? Run the server, okay? So fire the promise, so intersect that actions, fire the AJAX, fire the promise or AJAX request, and then fire the real action afterwards. This is something beautiful as a way to know and be able to describe, because here is when you now is put your async logic, async behavior separate from the act of updating. So once you get that data, is that you can now actually update the data. So the main use case for using middleware is like for logins, log customer behavior. So for example, based on navigations, or also logs actions, as well as putting side effect logics. So for example, like routings or HTTP like routings, or turn an async API calls into a series of synchronous actions. Interesting. So now let's get into this. So there are now actually other middlewares. So for example, famous middlewares are Redux Thunks, okay, Interesting. Writing logic with thunks. Okay, and we need to know what the F is a thunk, right? The word thunk is a programming term that means a piece of code that does some delay work. Rather than executing some logic, we can write a function body or code that can be used to perform the work later. Exactly. Rather than execute some logic now, we can write a function body or code that can be used to perform the work later, once you get the data. So, okay. And once, that's why the promise and that kind of thing kicks in. Because this is as a way to solve this specific problem. For Redux, especially, thunks are a pattern for writing function with logic inside that can interact with Redux store, dispatch, and get states. In other words, this is a way of how you can say, hey, this logic that I'm writing here, I want to now interact with the dispatch and then do something once that is done. So using thunks requires the Redux thunk middleware to be added to the Redux store as a part of its configuration. Thunks are a standard approach for writing async logic in Redux app. And why is this? Remember that after all, if you want to write async behaviors, keep them separate from the act of updating. Once you get the data, all right, now you want to do now you want to run a callback. You want to do some instructions, some functions here, and are commonly used for data fetching, right? However, they can be used for a variety of tasks and can contain both synchronous and asynchronous logic. So writing a thunk, as you can see here, is this, in this particular case, okay? So thunk is this particular functions that now can receive the dispatch and the get state, right? So thunk function, logic here that can dispatch actions or read the state. A thunk function may contain an arbitrary logic, sync or async, and can call dispatch or get state at any time. So, for example, in this particular case, right, in the same way the Redux code normally use actions creator to generate actions object for dispatching as a way to simplify that particular process, sorry, yeah, I have some fleas in my house. Well, this is not my house, but yeah, I got fleas here. The previous renter was not that. Hygiene was not a priority for him. That's all I can say. Hygiene was not a priority for him. And well, welcome to my lab. Okay. Coño, qué arrecho. De 300 puntos, qué loco. Una buena, y Valentín hizo casi 100. Rayos, usted es bueno, yo. Chanfles, usted es buena. Usted es buena, usted es buena. God damn it, man. Ah, perdón. Okay, exactly. So for example is this. So what you can do here is that once you get that, alright, Thunk actions creator and Thunk function. So here you say fetch to do by ID, right? Fetch to do by ID Thunk. Okay, you're gonna return this async function here. So once you are done with that, then is when you're going to update the state logic here, right? So writing Thunk using arrow functions like this is like, hey, let's go to define now this function that is, let's go to define this time independent wrapper around a value, okay? And once you get that value, okay, so once you get that value, then is when we're going to now triggering is this logic, right? So that's something interesting to do. Why use Thunk? Thunks allow you to write additional Redux related logic separate from the UI. So it means that you can now decoupling is the business logic, this state management from the UI. So make it much more easy to test. This logic can include side effects such as async requests or generating random value, as well as logic that require dispatching multiple actions or access the Redux store. Redux reducer must not contain side effects, not at all. They must be, because they must update the logic synchronous. But real application require logic that has side effects. So some of that may live inside a component, but some may need to live outside of the UI layer. Because of this, Thunks and other Redux middleware give us a place to put those side effects. It's common to have logic directly in your components, such as making an async request in a client handler or use effect hook, which is that's what allows is to actually is perform this side effect per React components, okay? And then now solve of the most common issues that you are when handling is side effects, which is network duplications, network duplications, caching, network waterfall, and not to mention race conditions. Because if you're now triggering is this async operations, and there is no way to actually stop them or abort them, okay, then you need to find a way to actually do that. That's what we use is the this particular flag to check if it is loaded, to check if this is now a data that we need to discard based on these race conditions. So what is the latest data that we need to get? And then processing the results. However, it is often necessary to move as much of that logic as possible outside the UI layer. This may be done to improve the stability of the logic, to keep the UI layer a thing as presentational as possible, or to improve code reusable and sharing. In a sense, a thunk is a loophole where you can write any code that needs to interact with the Redux store ahead of time without needing to know which Redux store will be used. So no matter which Redux store, no matter which state you want to interact or update your logic, Redux thunks allow you to now, oh man, the coupling is that from the implementations. So you want to trigger now this async operations, or you need to write code that needs to interact with the Redux store, usually in async mode. This is how can we do that. Thunks connect and container components. So because thunks is a general purpose tool that can contain arbitrary logic and they can be used for a wide variety of purpose, the most common use case are moving complex logic out of the component, making async requests or async logic, writing logic that needs to dispatch multiple actions in a row over time, interesting. Or writing logic that need to access the get state to make decisions or include other state values in an action. Thunks are one-shot functions with no sense of a life cycle. They also cannot see other dispatch actions, so they should not generally be used for initialized persisting connections like WebSockets. You can use them to respond to other actions. Thunks are best used for complex synchronous logic and simply to moderate async logic, such as making a standard AJAX request and dispatching actions based on the result of that. So this particular use cases of this middleware called Thunk or Redux Thunk is for actually is most of the time separate the logic from the UI component and put this logic or making async requests or other async logic. So writing logic that need to dispatch multiple actions in a row over time. Interesting. And writing logic that need to get the state out of this. So how does a middleware works in this case? Exactly, this is how a middleware you actually get. You initially get the store, which only can have access to dispatch and get state, followed by the next, which is, hey, this is what you're gonna do once we already run this code. I want you to go to the next middleware, and then the action that you want to trigger that, right? Exactly, so way to call this. If the action is actually a function instead, then call the function and pass dispatch and get as an argument. Otherwise, it is a normal action, so saying it onwards. Injecting config value into thunks. Think usage pattern, dispatching actions, accessing a state. Exactly, can be synchronous or asynchronous for that. Async logic and side effects. So after all, you are wrapping is a function with another function here. And what you are effectively creating is a closure for that. So doing this is you are creating now a closure of this function that can have access to the outer lexical scope, that can have access to this particular data. And when that data is, and then you perform your logic or async logic, and once you do that, now you want is to actually run that function with whatever needs and pass that to dispatch that action. Returning values from thunks. That's quite interesting. Using create async thunk. Now it's slowly but progressively started to make sense of this create async thunk. It's like now this is not synchronous logic, right? Now this is a time independent wrapper around a value, okay? Which is writing async logic with thunks can be somewhat tedious. Exactly, because you have to repeat yourself in this case, in the sense of defining is a function, defining is a function followed by the arguments as well as the async logic that you want to do, usually for the API calls, all right? And then dispatch the actions. This is something that you're gonna do a lot. And this is one of the most use case on this Redux store applications. As a way to trigger now is this Ajax request or fetch HTTP, right? So because of that, okay, each thunk typically requires defining 3 different actions type. Matching creators, pending fulfill and reject. Now you have to deal with this, plus the actual thunk creator, the action that is going to mutate, that tells the reducer to mutate that, and the thunk function is this independent wrapper around a value. There's also the edge case with error handling to deal with. So Redux Toolkit, so this particular middleware has now this thing called has a create async API, async thunk API that abstract the process of generating those actions for those 3 actions when doing these async operations, as well as the actual action, all right? And then the thunk function. And then the thunk function is that, hey, this is what I want you to now trigger once you get that data available. That abstract the process. That's why because software engineers live in a world of abstractions, that's what we need to understand. How do we get here? Holy crap. That abstract the process of generating those actions. Dispatch them based on a promise life cycle. And handling error correctly. It accepts a partial action type string used to generate actions type for pending, fulfill, and reject. Okay, which is great. It's like how you want to deal with this. And a payload creation callback that does the actual async request and returns a promise. It then automatically dispatches the actions before and after the request with the right, and it then automatically dispatches the actions before and after the request with the right arguments. Since this is an abstraction for the specific use case of async requests, a very specific use case of async request, create thunk does not address all possible use case for thunk. If you need to write synchronous logic or other custom behavior, you should still write a normal thunk by hand yourself. But it cover is this most common use case, which is async requests, which is this. So you say, hey, create async thunk with the name of the action that you want to do, and now the function that you want to run, and the function or the thunk that you want to run, followed by the proper, that's interesting, followed by the proper actions type, followed by the common actions type when handling async operations. So whether it's actions, whether it's pending, fulfill, or rejected. And then return the data that you need to. All right. So once you get the data that you need to, fetch to do pending and fetch to do fulfill, and there you got it. Oh, crap. Because after all this build or add case, this is now Redux. Exactly. This is now Redux toolkit. Exactly. This is now Redux, but we are using is Redux toolkit here, right? When we're creating this slide, this is state, all right. We contain is the initial value, the reducers, as well as the name slides, and hitting the extra reducer, you say, hey, let me add some cases, some actions here where we need to handle is this async operation, this particular way. Okay. And they're going to provide now is this common actions. Hey, it is pending. Hey, it is fulfilled. All right, then you're going to now is update the state line. Fetching data with RTKey query. But this is now using is create async Thunk for that. Fetching data with RTKey query is this. Redux toolkit has the RTKey query data fetching API. Interesting. And all of this is a Thunk. All of this is a Thunk. Okay. So Redux toolkit has a new RTKey query data fetching API. Okay. RTKey query is a purpose built that is a purpose built data fetching and catching solution for Redux apps, and can eliminate the need to write any thunks or reducers to manage data fetching, which is something that we're doing here on foot, right? We need to say, hey, I want you to know handling is this specific async operations when it comes to update our states, and this is the things that we need to do, which is the most common things. Create 3 types of actions to handle async operations, the proper actions, as well as the reducer, as well as the thunk, which say is like, let me now wrap this functionality, and when that is done, all right, I want you to now give me is the output of, I want you to now is provide me the value, provide me so after we get the value, now we're going to actually update the state in this particular case. But after all, thunks is just a time independent wrapper around a value. Okay, so fetching data with RTKey query is to cover that particular use. RTKey query actually use creating thunks, which is this function that allows to create these 3 common actions for handling async operations. The current action that is going to dispatch, as well as the thunk. These functions around, these time independent functions around a value, which means that I'm going to now run this function when that is, when the async operation is done. I want you to now dispatch this. I want you to run out this thunk. this function, this time-independent functions around a value. There is a lot of concept here, man. Jesus. RTK query actually use creating thunks internally for all requests, along with a custom middleware to manage cache data lifetime. Okay, interesting. So it not only handle is requests, data fetching, but it also is a caching solution, along with a custom middleware to manage cache data lifetime. First, create an API slice. This is from RTK with definition for the server endpoints. With definition from the server endpoints, fetch based query. With definition with the with the server endpoints, your app will talk to. Each endpoint will auto generate a React hook with a name based on the endpoint. So it generating now a React hook for that. Okay, this is pretty much like when we look at once this user action, when we look at the actions creator bind actions creator, right? Is now internally is creating now a functions with a prefix that now contain is these endpoints, and that is that exactly that now contain is this async logic for that. Oh my god. And then add the API slice reducer, and then add the API reducer here, the Pokemon API create API. There you go. Use Pokemon name Pokemon by name query. Okay, get Pokemon by name query. You know, it creates a hooks behind the scenes for that. So then you say, hey, the reducer path, okay, for this, okay, the update logic for this async operations, okay, which is now Pokemon API, Pokemon API.reduce path, and add a middleware to handle now is the cache validation, invalidation, polling, and other useful features of RTK query. Interesting. Finally, import the auto-generated React hook into your component and call it. The hook will automatically fetch data when the components mount. And if multiple components use the same hook with the same arguments, they will share the cache resource. So for example, once you can now have access to this store and you want to make use of this async update logic or this reducer, this async update logic, okay, or this Thunk, all right. Now you can have access to that particular slice, and then you say, hey, I want you to now query that data in my components. That is going to provide you now is the data, the error, and this loading for that, and the rendering logic. Holy fuck! Jesus! Oh my god! The question here is that let's see what is a Redux, a Thunk here. You know, let's go to actually check what a Thunk it is at the end of the day. Jesus fucking Christ. Holy moly, bro. That's freaking well. Okay. So how to dispatch an action? Oh my god. Why do we need a middleware for async flow? Oh man. Okay. What do you think it is? Hmm. There's another question here. Is that yeah, but how can we create now a thunk? How can we create now a thunk? Let's get into this. Let's get into this. Let's French toast get into this. Let's French toast get into this. Extracting impurity, containing impurity. Let's French toast get into this. Immutability, recursion, map and transform, transduction, and async and lazy. Okay. Jesus. Low-FP, Lambda, and FBO. Reactive programming with Redux. I don't think this is something that we get this. We have now that in Thunks. Holy crap. Thunks enclosures. Here we are. Let's get into this, my friend. Let's get into this, bro. Okay, the callback help, right?
We're going to look at some problems. That brings us to this idea of concurrency. What does concurrency mean? A lot of people would think concurrent means two things happening at the same time. Again, it's one of those things, if you squint at it, you might say, yeah, okay, maybe they're kind of like the same, but there's an important nuanced difference here. And by the way, if somebody wants to object to my particular usage of the words, there's actually lots of different meanings for these words, and it's hard to nail down one particular thing. So I'm trying to be as consistent within my own usage of these things. But there's actually, if you go and read Wikipedia pages or other texts on it, you'll find a whole range of different opinions on these things. But my way of explaining to you what concurrency is, rather than saying with parallelism, two things are happening at the exact same instant, I would describe concurrency as two higher level tasks happening within the same time frame. So rather than an instant, we're going to look at a time frame, and we're going to say within this time frame, two higher level operations are going to occur. To understand the notion of higher level items or higher level operations occurring, we also have to understand that higher level, or what I might call like macro level tasks, can be broken up or thought of as being broken up into micro level tasks. So here's a way to visualize the macro level and the micro level and how these things might go together. So on the left-hand side, we have this yellow-orange task, or the macro level task, which is broken up into those individual numbers, 1, 2, 3, 4, which would be micro level tasks. These are my made-up terms. These aren't official terms, but macro level and micro level tasks. Okay? And then on the right-hand side, we have another macro level task represented by that blue-green color, and it's broken up into 3 pieces, 1, 2, 3. Now, for the easiness of math, I'm going to pretend and assume that each one of these micro level tasks takes 1 full second to complete. So this overall system, to do all of the tasks, it's going to take 7 seconds. Does everybody agree with that? Because it's a single-threaded system, nothing can happen at exactly the same moment, so those 1 second micro-level tasks are going to have to be scheduled in some way that all 7 of them finish, and that's going to take 7 seconds. Let's pretend nothing can happen at exactly the same moment, so those 1 second micro-level tasks are going to have to be scheduled in some way that all 7 of them finish, and that's going to take 7 seconds. Let's pretend that the yellow-orange represents an AJAX request and response cycle. Fire off a request, we get a response back. And let's pretend that the blue represents a scroll, that we scrolled on the page and it repainted everything because we scrolled to a new location on the page. These two operations have to fundamentally happen on the same thread. The entire user interface of our browser is happening on the same thread. So our JavaScript, the garbage collector, the style engine, the repaint, everything, it's all happening on one thread. Which means we kind of have to worry about contention. And if you've ever had an animation on your page have jitter in it, you know why that happened? Because something contended on the UI thread. At that moment, your CSS engine was trying to, or your layout engine was trying to repaint the page. It's 60 frames a second way that it's repainting your page. It tried to do that, but at that exact moment, something else was running. So it had to wait an extra moment, and that's what created that jitter. Single threaded. So if we have these higher level, macro level tasks that we want to happen concurrently, I want the yellow and the blue to happen at the same time. Why? Well, let's imagine they don't. One way of scheduling this system, one way of scheduling this program, is to do all of the yellow first and then all of the blue. What would that look like on our page? Ignoring the 1 second thing for a moment, what it would look like on our page is that it would look like I clicked the button to make an AJAX request, And while that was happening, I tried to scroll my page, but everything was completely frozen while that happened. And then after it finished, then it sort of, jumped back and caught up. We actually have precedent for that. It's called synchronous XHR, synchronous AJAX. One of the worst evils perpetrated upon the web platform. It's a terrible idea. There are people out there that are crying and literally complaining on standards lists saying, how dare you take away my synchronous XHR? It's been deprecated and removed from the web platform because it's a really bad idea. It's a terrible idea to schedule it that way, isn't it? Because even though the overall system would still take 7 seconds, that particular choice of scheduling those micro-level tasks would feel terribly inefficient. Does everybody agree with that? Just from a user experience perspective. If, on the other hand, we chose to interleave these things together, where one thing might be blocking so we can do something else while one thing is blocking before it can move on to the next thing, if we chose to schedule those things in an interleaved fashion, the overall system might still, in fact, take 7 seconds. But the perception of the performance is that things are going to be happening in parallel. Really, more importantly, we should be saying those things are happening concurrently. The AJAX and request and response is happening concurrently with the repainting, even though at any given instant, only one of those micro-level tasks is occurring. So, just to visualize that, my fancy animation took me about 2 hours to get right in Keynote. Here's a way of scheduling those micro-level tasks onto that single thread in the middle called the event loop. I don't know why that advanced. The single thread in the middle called the event loop. That's what we call it in JavaScript. At any given instant, it's only doing one of those things. So when you have an AJAX request that comes back and you need to fire the callback for a response, if at that moment somebody's already executing, nobody gets to cut in line. Right? It's not like your response callback gets to interrupt and say, oh, it's time for me to run. You know what it does? It gets at the end of the line, just like everybody else. So when the garbage collector says, I need to collect some garbage, and the style CSS repainter says, I need to repaint the page, and the layout engine says, I need to do some work, and the JavaScript engine says, I need to fire this response callback, and every single one of them, it's a first come, first serve, everybody gets at the end of the line. That is fundamentally what the event loop is. Okay? So that's just a high-level view to help you sort out what's going on. And the main point here is that the scheduling of this is not always entirely within our control. Sometimes it's race conditions that choose one versus the other happening. Not all of that's happening, but there's an awful lot of coordination necessary. Sometimes it's the coordination of when things happen, but oftentimes it's the coordination of responses to things happening. Because it's not always a very serial, like do this, and then when that's finished, do this, and then when that's finished, do that. Oftentimes it's much more complex, like, hey, go do these 3 things in parallel, and then when at least 2 of them have finished, you can move on and do this other thing, and then when that 3rd one comes along, you can branch out here and do this other thing. And before long, it's just crazy complex tree of different states of things that can happen. And it's that complexity that we have to manage in our programs. It's that complexity that begs for us to have better patterns for concurrency management. That's what asynchronous programming is, managing our concurrency. Okay? So that's a motivation for you from a philosophical and conceptual basis, a motivation for why we go to the lengths that we do to try to write the programs that we do. Everything that I'm going to show you in this workshop is something that could fundamentally be done with nothing but the callback. There's no new functionality here. But we're going to see that the callbacks fundamentally are insufficient for expressing the higher and higher orders of complexity that are modern.
So, interesting. Oh my God. So callbacks are insufficient to express now this async nature of coordinating the complexity of these applications. In other words, is that it's insufficient to now coordinate when all of this async stuff needs to happen in one way, right? And that's why we're starting to see now different. That's why we need to focus on different patterns that allow us to handle or to delegate that to that.
And JavaScript programs are doing. Our modern JavaScript programs are falling all over themselves because we need these higher order patterns, and we're not disciplined enough to learn them and implement them. We just keep doing the same thing we've always done because it always worked and it always worked and it always worked. This is a call to arms to say the new baseline of competency as a JavaScript developer is to have a much more sophisticated, strategic, and tactical approach to your concurrency management, to your asynchronous program. Our modern JavaScript programs are falling all over themselves because we need these higher order patterns, and we're not disciplined enough to learn them and implement them. We just keep doing the same thing we've always done because it always worked and it always worked and it always worked. This is a call to arms to say the new baseline of
This is a call out to arms.
Competency as a JavaScript developer is to have a much more sophisticated, strategic, and tactical approach to your concurrency management, to your asynchronous program. we're going to look at some problems with callbacks. We're going to get some practice with them, and then I'm going to articulate to you the real essence of what callback hell is about. But I want to look at some issues with callback.
Exactly. It's because
it brings us to this idea of
like, yeah, we're handling is now this async operation. We look at thunks. We look at thunks and we say, great, but oh my god, jeez, there's a lot of it, and I love it. Let me actually get into this. So, because I'm looking at Thunk, and Thunk is this functions that allow us to handle this specific updates that allows to handle is async behaviors when it comes to need to update our state synchronous. Why we need to do that? Because when we are able to do those state mutations synchronous, we can now have a better log, a better record of how our state are mutated. So we can look at that, and we can also maintain that much more easy. But life is not synchronous, right? Life is, in the context, you actually need to deal with a lot of asynchronous stuff, as you said, right? So when you go out and then you ask for an Uber, even though once you get that Uber and it's waiting outside of your house, then you go out and then you actually is to check if you have the keys, you have any other paper on your cell phone, or you have your purse, you have if you're going to go to work, if you have now the credentials with you, as well as the laptop, you need to take that away. You know, there's several things that you need to handle to reach there that also are not contemplating that. So as you're getting into your Uber, let's say there is some riot on the streets, you didn't think about it, you didn't expect that, and then you have to pay the Uber and find a way to get out of the car and cross the streets and to the job and that kind of thing, right? And then you find, let's say, someone actually asks you money on the streets. You decide to giving a gum chunk that you have because you are very busy to get to your job, and there's a lot of things that can going on as you go to a particular place or you reach a goal. So for example, it's like this. It's like there is a lot of things that we need to handle, that I need to take care of, and it is your responsibility to get it, right? It's not your fault that what it is, but it's your responsibility to get it. So in any case, what doesn't mean is that we need to look at this thunk. We need to understand what this thunk is, and we need to understand is what asynchronicity or concurrency means when we need to actually manage this complexity. Oh, here we go. Oh, here we go. Question: asynchronicity in JavaScript, right? Because so far we are good at understanding is what is this language is doing, right? We understand is how it allows us to create objects, a way to represent things. So we know is the variables creations and control flow mechanisms and loop and iterations, and then how now you can create objects, what objects is, the object-oriented programming, then how you can now use is as a way to reuse all of this object using the prototype inheritance, and how that works behind the scenes. And then we reach now to the point of concurrency or asynchronous things. I want to read is from the I think it's eloquent in JavaScript, right? values, program structure, functions, object, high-order function, the secret life of objects, which is the object-oriented programming or the prototype here. An abstract data type is realized by writing in a special kind of program. This is abstract data types, right? Prototypes, classes, right? Oh, but this is actually updated. Okay, private property. Overriding the right properties. And maps. Okay, this is the new 4th edition. God damn it. Okay. Jesus. Project a robot, box and arrow, regular expression models, a synchronous program. Okay. Who can wait quietly while the mud settles? Who can remain still until the moment of actions? Lao Tzu Tao Te Ching. Who the fuck is this? Here we go. Tao Te Ching. Ooh, okay. El Dao. Dinastía Su. Del Taoísmo. Here we go. The art of flow of art. Neoconfucianismo. El Dao o el camino. Oh my god, this is the way. De. Dao de Yin. Dao de Jing. El libro del camino y la virtud. El libro del camino y el poder. Leer. Pero anterior a la escritura de Xuan Jin. Existe un debate académico sobre la autoría de la versión actual del Dao de Jing. Se han hallado secciones bajo la forma actual en tablillas grabadas en piedra alrededor del 300 de Cristo. Textos de Manguadí en seda. En tira de bambú. Textos de Wodian. Damn, son. El Tao. Mm. Lo que persigue este huye de frente, mira. Oh, shit. Huevona, el popular. Solo sé que no sé nada, man. Only know I know that I know nothing. Cuando perdemos los valores. El DAO. Mr. DAO, ok. Okay. And it all boils down is from asynchronous nature. Okay. The central part of a computer, the parts that carry out of the individual step that make up our program, it is called processor. So this processor, or this person that can take all of these individual steps that takes program, okay, or run it, is the processor. Look at them as an individual, as a person, right? Is the processor. You can call this as the God, the Zeus, or any whatever God you wanna call it. But it's the processor. So the programs we have seen so far will keep the processor busy until they have finished their work. The speed at which something like a loop that manipulates numbers that can be executed depends pretty much entirely on the speed of the computer's processors and memory. How fast are you to process all of these series of steps with the memory that you have? But many programs interact with things outside of the processor. For example, they may communicate over a computer network or request data from the hard disk, which is a lot slower than getting it from memory, right? So when such a thing is happening, it will be a shame to let the processor sit idle. Exactly. Say, please, I want you to keep continuous doing things. There might be some other work it could be it could do in the meantime. In parts, this is handled by your operating system, which will switch the processors between multiple running programs. But that doesn't help when we want a single program to be able to make progress while it is waiting for its network requests. So for several things that you need to do in other programs, yes. But when we need to wait for other things on one program, on one series of steps, that's not ideal. That doesn't help. So in synchronous programming model, things happens one at a time. And then when you speed that up, you get the outcome that you want. When you call a function that performs a long-running action, it returns only when the action has finished and it can return the result. This is stop your program from the time the action takes, right? And asynchronous model allow you multiple things to happen at the same time. Or at least this is the conception here. It allows you to do multiple things at the same time. For example, but at the same time. This is something that perhaps in the human perspective is quite hard to get it. Because doing multiple things at the same time is like, for example, you are walking. When you are running, your body needs to perform the actions to put a leg in front of the other, breathe, be aware of what you are doing because you don't want to hurt yourself, and other things that need to happen to your skeletal muscle. There is a lot of things that needs to be done in that, right? So, makes sense. So when you start an action, your programs continue to run. When the action finishes, the program is enforced to get access to the result. For example, the data read from disk. We can compare synchronous and asynchronous program using a small example. A program that makes two requests over the network and then combine the results. In synchronous environments where the request function returns only after it has done its work, the easiest way to perform this task is to make the requests one after the another. And it has a drawback that the second request will start only when the first has finished. Hey, I'm going to now run this 2-second operation, but once the first is done, so the total time taken will be at least the sum of the two response. This is on synchronous environments, one after the other, sequentials. So the solution to this problem is in a synchronous system is to store additional threads of control. Another Okay, another threat of control. Another callback key, another cue or threat of control. A threat is another running program whose execution may be interleaved with other programs by operating systems. Since most modern computers contain multiple processors, right? Multiple threads or multiple thread controls could start the second request, and then both threads wait for the result to come back, after which they resynchronize to combine the results, which is exactly in a single thread. You say synchronous, you have to wait for that until you get the data and then continue to that. And asynchronous with threads, what you're doing is that, hey, I'm going to now run is this async operations and then the another, and when that time you get that, all right, I'm going to process that. But in asynchronous here, another way to describe this, but exactly, synchronous through thread of control, which is what happened here with Node. Another way to describe the difference is that waiting for actions to finish is implicit in the synchronous model, while it is explicit under our control in a synchronous one. Asynchronicity could both ways, and it makes expressing programs that do not fit the streamlined model of control easier. But it can also make expressing programs that do follow a streamlined more awkward. Completely. We'll see some way to reduce this awkwardness later in the chapter. Both prominent JavaScript programming platforms, the browser and Node.js, make operations that might take a while asynchronous rather than rely on threads. Exactly. So rather than relying on thread, which is something that, for example, PHP actually is doing, or other particularly programming language are handling asynchronicity, is like, hey, I'm going to do this now. Exactly, JavaScript environments now have a very particular way to handle this. Since programming with threads is notoriously hard, understanding what a program does is much more difficult when it's doing multiple things at once. This is generally considered a good thing, because if you have multiple programs, okay, because it reads. So reads now a program that makes multiple things, okay, and then understand the output once, is generally considered. So callbacks. That's what we have this. One approach to this asynchronous programming is to make functions that need to wait for something take an extra argument, a callback function, right? And the other is a promise. A slightly different way to build an asynchronous program is to have asynchronous functions return an object that represents its future result instead of passing around a callback function. This way, such functions actually return something meaningful, and the shape of the program more closely resembles that asynchronous programs. This is why the standard class promise is 4. Exactly. So far, so good. No problem with that. And the other is failure. Regular JavaScript competition can fail by throwing in sections here. All right. This is now explaining that and that kind of thing. So breaking in, and this is now describing is just a particular function here, and the generators. This ability of functions to be paused and then resumed again is not exclusive. The async functions, JavaScript also have a feature called generator functions. They are similar but without the promise. When you define a function with function placing an asterisk afterward, it becomes a generator. When you call a generator, it returns an iterator, which we saw in the chapter 6. And this iterator is now an object that represents is an object that follow is the iterator protocol and iterable. The iterable protocol. Where this, okay, of the abstract type, the method, the prototype, the classes, right? Private property, overriding the right property, maps, polymorphism, getters and setters and statics, symbols, the iterator interface, exactly, which is a particularly designed pattern for getting values out of this. So this is the list and the list iterator for this. So we are quite familiar with that, right? Initially, when you call powers, the function is frozen and it is a star. Every time you call the next iteration, this is how you can indicate that this particular objects now will implement that specific behavior, iterating behavior. The synchronous program start by running in the main script will often set up callbacks to be called later. In the synchronous bug. But in any case, we are here by looking at the working
concurrency. A lot of people would think concurrent means two things happening at the same time. Again, it's one of those things, if you squint at it, you might say, yeah, okay, maybe they're kind of like the same, but there's an important nuanced difference here. And by the way, if somebody wants to object to my particular usage of the words, there's actually lots of different meanings for these words, and it's hard to nail down one particular thing. So I'm trying to be as consistent within my own usage of these things. But there's actually, if you go and read Wikipedia pages or other texts on it, you'll find a whole range of different opinions on these things. But my way of explaining to you what concurrency is, rather than saying with parallelism, two things are happening at the exact same instant, I would describe concurrency as two higher level tasks happening within the same time frame. So rather than in an instant, we're going to look at a time frame, and we're going to say within this time frame, two higher level operations are going to occur. To understand the notion of higher level items or higher level operations occurring, we also have to understand that higher level, or what I might call like macro level tasks, can be broken up or thought of as being broken up into micro level tasks. So here's a way to visualize the macro level and the micro level and how these things might go together. So on the left-hand side, we have this yellow-orange as two higher level tasks happening within
two high level tasks
the same time frame.
Okay, and I don't want to dive deep too much of this. I'm just here is for the thunks. Okay.
The second tenet of callback L, I'm going to fundamentally declare or assert that callbacks are not reasonable. And I highlight reason to suggest. I don't mean reasonable in the sense of like likable. I mean reasonable. They are not able to be reasoned about. Let me try to illustrate. How many of you have ever heard before or said before yourself, I'm a multitasker? Anybody ever said that before? It's pretty common. People talk about it. I'm like, I'm driving down the street, I'm talking on the phone and texting, I have my laptop in the seat next to me and listening to the radio and mom's on the phone, like doing a whole bunch of stuff. I'm multitasking. Well, that's nonsense. We're not actually multitaskers. At our highest level of cognition, which is the only part that I care about right now, I'm not a neuroscientist, so I'm not really speaking as a neuroscientist, but from what I know and from what we can observe, at our highest level of cognition, our brains are fundamentally single-threaded. At any given instant, our brain is only thinking about and cognitively thinking about one exact thing. Plenty of other parts of our brain are taking care of all the other autosomic things like our heart and breathing and all that other stuff. I'm not talking about that. I'm talking about the highest level of cognition, the part where we are intentionally planning and thinking about things. And at that part, we're only thinking about one thing at that exact moment. So let's imagine this morning when you all woke up. This morning you thought to yourself, I got to plan out my day. So when you woke up, you started planning out your day like, well, I got to get some coffee and I'll hop in the shower and then I'll get on the, get in the car and drive to work and then I'll head over to this workshop. And you planned out your day in a very sequential, step-by-step fashion. Mm-hmm. Virtually all of us, our brains, we'd say that's how our brains work. We think about things in a very sequential fashion. However, I'm also willing to bet that virtually none of you had your morning play out exactly the way you planned. You were up making some coffee, and then your mom called, so you got interrupted by that call. That wasn't part of the plan, and then this other stuff happened, and your car was out of gas, and your plan had to change. And thankfully, you didn't have, when your mom called, you'd be like, well, there's the whole day shot. I didn't plan for that, so I better just go back to bed and start up tomorrow. Your brain, thankfully, is, interestingly, a lot like the JavaScript engine in that it can be interrupted event-wise, like an event loop. You can have an event fire, and it can choose to respond and adjust. But that's not the part we care about. The part that we care about here is the part of our cognition where we plan things. And fundamentally, what I'm going to argue is that we naturally plan things in a sequential, synchronous, step-by-step fashion. So, if that's how we plan things, that's also how we code, most naturally. Now, I have a theory here. This is not a law. It's as close to as proven a law as I can probably get. I have this theory that any place where our brain diverges from the way the JavaScript engine works, at that moment where the two diverge, it is at that moment that bugs happen in our code. Wherever our brains diverge from the way the JavaScript engine works, I can't do anything about how the JavaScript engine works. It just works that way. I can teach you better about it, try to train your brains better, but I can also try to offer you patterns that allow you to program more naturally like your brain so that there are hopefully less bugs in your program. That's basically my theory of teaching. How do I train you to write your code so that it works more like your brain, so that there's less divergence and less bugs? So it's more reasonable. It's more.
How do I train your brain, or how, in this case, how you can share your knowledge as a way to now write programs, write sequence of data that work with your brain? Oh shit. And the question is that why do we want to know that? Well, because again, this is part of the opportunity that I want to get, and also to understand, truly understand how to do that as a way to solve these particular common problems in my daily life, and then have time to explore.
Understandable. We see callbacks don't really offer us much affordance in that way, because we could think about it from a pseudo-task perspective. Like, you know what I love about pseudocode? Pseudocode's awesome because you just get to invent magical stuff out of thin air. I wish I could get paid to write pseudocode all day because it'd be the funnest job in the world. I get to invent stuff like on line 3 where I invent pause. This magical thing that I invoke called pause, which doesn't actually exist, but it doesn't matter because this is pseudocode. And then on line 9, I invent this other thing that also doesn't exist called resume. I just magically pick up where line 3 left off, right? That's how I'd write this out in pseudocode. But as soon as a developer got hold of it, he said, oh, no, this, you're just making stuff up. This is not how it works. So they begin to rearrange things, and they might rearrange the pseudocode like that. They say, well, we can do this pause and resume thing, and then a pause and resume. And do you see what we've done now? We've started to implement this as a series of nested callbacks. Because callbacks alone, that's the only way for us to express, and listen, here's a fancy term for you, temporal dependency. When one thing depends upon another thing finishing before this thing can go, that's a temporal dependency. And the only way with callbacks for us to express temporal dependency is nesting one inside of the other. The call to one inside of the call to the other. Whether we do so with inline function expressions or with just the function calls, the only way to handle temporal dependency in callbacks alone is through nesting. Well, why is that such a problem? The reason it's such a problem is now your brain doesn't get to linearly progress through the code. Your brain has to do what I call non-local jumps. Here's a metaphor for you. How many of you remember way, way back, I'm talking like mid-80s, the original Nintendo? And my favorite game of all time on the original Nintendo, Legend of Zelda. Anybody remember? I had to leave the thing running, forever and play it. It would take weeks to play through or whatever. You know what I loved about that game, though? There's this one part. You would go into a cave, and all of a sudden the screen would go completely black, except for this tiny little circle around Link where he's holding his torch up. And you can see just a small little portion of the map at any given moment. Now you could move Link all over the cave. You could see the entire map, but only this little circle at a time. You could not see the entire thing all at once. That's what modern JavaScript programming is today. Modern asynchronous JavaScript programming. Now this is not a knock on any individual person listening to this to suggest that you are just fundamentally bad programmers. We are all limited in this fashion, that the complexity of asynchronous flow control that happens in our programs, there is no developer on your team that understands all of those flow paths. It's beyond our capacity to understand. You might get step 1, then step 2, then step 3, but as soon as you get like step 1, 2, and 3 at the same time, and when these two finish, fire off here and there, you're completely lost. You can understand only just this small little portion. You get that, and then you move over here and you understand this part, and then you move over here and you understand this part.
And then go to the next one.
And heaven forbid, when those parts are where the callbacks are jumping around between the files of your program, and you are fundamentally not able to plan out your program the way your brain works. Because callbacks alone don't have a way of expressing things in a sequential, synchronous-looking fashion. It seems like it's almost impossible to do, doesn't it? Doesn't that seem like almost a unicorn? Like, there's no way to do asynchronous coding in a synchronous fashion. That's like having false be true at the same time. That seems impossible. Well, I'm going to all the trouble to talk about this to suggest actually it is quite possible. But that's why we need a better pattern. Because what we need to do to solve...
Because we're talking about here a particular problem. We're talking about here a particular problem, and that problem is when you're writing these particular applications or programs, series of steps that is executing one after another, as resembling the same way of human brain, okay, to actually solve these particular problems fast as possible. The thing here is that when you need to handle is this async nature, or this thing that are two things or multiple things that needs to happen at some point in the future. Yeah. When you are writing now things in this particular order or this time-dependent programs, which is, hey, is this function, is this series of is this instruction needs to run after the next one, and so on and so on and so forth. So that's one of the reasons why, well, yeah, I'm agree with what he mentioned, which is you are now have to debug, you are now to read where all of these things happens, and then you completely lost. So that's why we need here is a better pattern, is a better approach when we read these kind of applications. At least initially here right now, because again, we have inherit all of the things, we like it or not, this is the way how things works. And again, this is not talking about is synchronicity. Synchronous and asynchronous JavaScript. So the more familiar you are with this particular way of describing sentence and series of steps, the more sense it'll be for you to do. And then some other problems that come
Callback hell is to be able to express our code in a synchronous sequential fashion the way our brains think. So when we write code like that, first half of my program, then the second half of my program, and we think to ourselves that it's like blocking 1,000 milliseconds, which doesn't really exist, and the JavaScript engine says, actually, I'm going to do a whole bunch of other stuff during that. What we need to do is restore the ability to express things in a synchronous, sequential-looking fashion.
Synchronous, sequential, and blocking fashion. Again, this is to improve the readability. This is to actually be able to now, when you are writing your code as a human, which is to be able to actually now do that aligns to the human brain.
That's the other part.
That's also the thing that I now is, well, dive deep into this particular topic as a way to understand how the thing especially works with Redux. With JavaScript, I now reasonably know for synchronous code, but when it comes to now understand how these asynchronous operations are happening, I don't have any clear, in terms of the implementation, for example, the async and await, because after all they're using is the language by that, I don't have any way of how can I describe that. Mm-hmm. 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 Mm-hmm.
For the callback hell that we need to fix to make our synchronous code fundamentally more reasonable. There's a bunch of non-fixes that have been attempted with callbacks. I call them non-fixes because they're attempts at fixing which actually did nothing but make it worse. So, for example,
Non-fixes.
in the callback world, we invented this pattern of split callbacks. If our problem that we're trying to solve is that we've got an error that we don't want to get swallowed in case there's some problem with the main function, we're like, oh, I know, I'll just pass a separate callback for my errors. And that way, if there is some error, at least I know that utility will have some way of notifying me that there was a problem. Right? Sounds good on the surface. Until you realize this actually makes the trust issue a lot worse. Because now you have to ask yourself, what happens if they call neither of these functions? What happens if they call both of these functions? Maybe they call the error first and then the success. Or maybe they call the success first and then the error. How's your program going to handle that? I bet some of you have code like this and you don't have any solution for that yet. It actually made the problem worse. There's more trust issues. So split callbacks, while it sounded good on the surface, actually was a regression. It took us away from a good solution. In the node world, we invented what oftentimes referred to as node style. I like to call error first style callbacks. They say, well, let's go back to one callback. 2 callbacks is crazy. Let's go back to 1 callback. But we'll reserve the first parameter of that callback for the error signal. So if it's an error that we're signaling, we'll always set that one and nothing else. And if it's not an error, then we'll leave that falsy. And so every single node callback that you've ever written has this if-else jazz going on in it, where you're checking to see whether or not it's an error condition or not. So it seems like it solved the problem about the split callbacks thing until you realize actually the same questions occur here. What happens if the utility in question does not behave the way you expect? What happens if it calls your callback twice, once with the error and once with not the error? Or what happens if it calls with both the error and the success parameters? How do you interpret that situation? All the same trust issues are at play. We are not fundamentally in control of the callback, which means we have inverted all that control and given it away to somebody else. So these are really non-fixes. Now I've got a silly running example. How many of you recognize the reference to the meaning of life? Hopefully I'm not so old that I'm the only one that knows about Hitchhiker's Guide. If you don't know about that, go read Wikipedia. Something, get up to speed on it. Silly example, calculating the meaning of life using nested callbacks. There's my fake Ajax call, my get data function. You notice it takes in a piece of data, like a number, and then after 1,000 milliseconds, it calls whatever callback I provided and just sends the data right back. Mm-hmm. So I pretend to ask for the answer, it's a calculation of value 10. 1,000 millisequents later, the function's called and num1 is the value 10. Now x is equal to 1 plus 10, so x is 11. And then I make the call to 30. You notice that this is sequential calling. I've nested these calls together because they have a temporal dependency. I can't calculate 31 until after I've calculated 11. Mm-hmm. And then after both of those have been calculated, then I put the two together, meaning of life 42. I ask for that I ask for that to be computed, and 1,000 milliseconds later I get my answer back, meaning of life 42. Yeah, sorry. We're talking about lines 5 and line 7 for the get data calls, line 9 for the get data call of meaning of life. And then finally the answer is coming back on line 11.
So if you pass that now here, so once you pass 1,000 milliseconds here, you're gonna run this particular callback, where that you are passing to this, where you say, hey, I'm going to now, the value that I'm passing here, which is 10, add 1, all right? And then I'm gonna call this function here. You may wonder that, hey, this is something that is going to execute that right away. But no, you have to wait 1,000 seconds. To do that, and here, because we're calling now this particular function, but now with 30 and passing now is this function num2 as an argument. We say, hey, now in this time is 30, and you want to apply that to 1, which is 31, and then you say, hey, the meaning of life is 11 plus 31, which is this is now the data, okay, and this is now the callback that you say, hey, now I get the answer. After 1 millisecond pass, you're gonna run is now imprint that, right? The meaning of life is. But what happened here is that it requires a lot of cognitive load here as a way to understand now how the thing works. This inversion control, this function that need to go out to another definition, read that, go back, runs that, read the definition, go back, and so on and so forth of this. For readability, it makes quite very
Hopefully mine only took 1,000 milliseconds
hard
to read
to
instead
read.
of trillions of years or whatever. That would be a pretty big number for the set timer. But you see here I have the nested callbacks, and I have all the problems of, this is non-local, non-sequential reasoning even. Yes, I can move through the pyramid, but what happens when I move one of those callbacks into another module of my utility? Now I've got this non-local jump over to some other location to understand what's happening. And I have all the trust issues of inversion of control.
A lot of trust
All right, let's talk
issues
about a pattern
in
on
inversion
top.
control.
There's a bunch of pretty big number for the set timer. But you see here I have the nested callbacks, and I have all the problems of, this is non-local, non-sequential reasoning even.
Exactly. This is non. All of these callbacks are non-sequential reasons of this.
Yes, I can move through the pyramid, but what happens when I move one of those callbacks into another module of my utility? Now I've got this non-local jump over to some other
Now I have this non-local jump to another
location to understand what's happening. And I have all the trust issues of inversion of control.
Inversion control. I have a trust issues with inversion control. Tengo problemas de confianza con la inversión de control. Oh my God. Jesus. God damn it, bro. And it is a design principle in which custom writing portion of a program computer receives the flow control from an external source, and the term inversion is historical. A software architecture with their designs inverts control as compared to procedural programming. And I get it why this is called inversion control. Because it's like an inversion control in the way how human perceive this particular code is like, hey, because we as human perceive things sequentials one after the other, right? And that might be somewhat delusional for ourselves, that we thought that things are in this sequence, and when we have much more control of all of this sequence, all this stuff can happen. Asynchronous stuff can happen. For example, you go out and you say, hey, let's go to now take some vacations to Rio, okay? So you actually have everything planned. You already know, your luggage ready, your time schedule to actually go out and take the Uber, and then reach a particular point to the airplanes, to actually board, departure from the airport, and then couple hours later you reach to another airport for transit, then you go next to another one. We can see all of the sequence steps that can happen, and we can have now control, or the sensation of control of this. But a lot of things can going on badly in each one of those states. So for example, you can have a riot during the Uber, all right? Or sometimes there is a storm, and you have to delay that a couple hours, or when you reach to Rio, it's now dark enough so you don't know even the language for that, and some people actually are close to you and they want to steal you. There is a lot of asynchronous things that we have to deal in this sequence, in this control flow. Okay. So this inverse control flow, it means that because you are not need to read this because we are naturally are inclined to understand things one after the another. And when we read our code and then we need to go after, we need to look at another model, so we have to jump to another model, to another thing, to come back here. That's when we started to have now trust issues with this inversion control. So in other words, we can see now that I understand what this inversion control means. So for example, if you want to create now an agent, if you want to mimic the functionality of the async and async by creating now a functor, which is a function that implements the iterable protocol, right? Which means is that here I want to run this particular code, which is, hey, this is the code that I want you to run, okay, when I call you. So in other words, so when I call you, I want to now receive that property, or in this case that callback, okay, and I want to assign that to let's say I want to receive that callback, all right, which will be naming convention. Jesus, name things is catching and naming things is one of the most hard things in computer programming, but it's let's gonna call this let's go to assign this to our result. All right, so once I get that, all right, because at the end of the day I want to now is return, in this case I want to now is or return or call that, whatever you're gonna call it, is these results. So once you get that, so this is now the callback, all right, and this is the results. So this callback that we are getting here as a result or result function, okay, we can say now I want you to run this functions. So once I call you with this, then I want you to now run is this. So this is now called as the generator. Let me actually see is the JavaScript hard parts of asynchronous JavaScript. It's like this. It's like this async generator stuff here, right? Because the idea here is that I want now to get the data, okay? So I want now is to perform the data here, make the async operation, which is, let's say, fetch to do I have some so I can say is wait for this, which means I'm gonna make this as an async functor, okay? So you're gonna get that data, you're gonna run this. So let's say, hey, I'm gonna get this. No, there is actually a placeholder API user, right? Where you say affect your placeholders like this, sponsor mockend and subload. That's right, there you got it. Wrong script to do, really? Okay, yep, that's exactly what I want to do. Okay, that's exactly what I want to do. So the idea here is to now So as a way to see what I'm doing here, okay, is this one. Yeah, as a way to see that what you are doing here is this one. I want you to now is on, because this async, and await syntax, right? So when you create now this function here, and then you say, hey, I want you to make this function, async function, okay? Where in this async function is one, I want you now is call this. No, it's not this. And when I call is this, okay? And that is, well, I want to get the data and I wait for that, right? But I want to await this data like so. And I want to await this data like so by using is now this fetch API, which is a great thing. Okay. So this is cons. So once you get that data, okay, I want to now actually log that data for this, right? So when I call this function here, let's gonna make this say, hey, run it. Async fetch, or in this case is get to do, or yeah, get to do ID, or get to do, right? So when I call this and I say, hey, line break, of course, damn it, there you got it. Oh, come on, don't act like that. Don't act like that. Don't act like that. Okay. And when you say get to do, because this is now an async function, all right, it means that we need to wait for that. So if we have now this top level await and async, that of course actually provide us as expected, right? But if we don't have that get to do here, all right, we need to somehow get into that function, which is this dot then. We need to actually say, hey, once you get that, I want to now console log is the data that you get. So once the promise is being resolved, when this async operation is being resolved, I want you to actually do this. Get to do dot then. Why not? Because I need to run this, and then is when you're gonna get this. Exactly. But the thing here is that because now we have this change of then, and we want to make the code readable as much as possible, align this to how we perceive things and how we can now sequentially these things, it is important for us to actually make that distinction, write line of codes that follow that sequential and blocking way of writing applications. So as a way to do that, they're now using some of this particular mechanism, which is using generators. All right, that's quite interesting. Is using generators as a way to do that, as a way to create this inverse control flow. As a way to solve this inverse control data. Why this is inverse control data? It's because of this. It's because of it, right? So yeah, let's go into define something like this. Okay, we already have this get to do, right? It's actually performing is now this. Okay. Yeah, and I want to do is this, right? I want to say, hey, promise, right? I want to now create a new promise here. Objects, okay? And that will contain is the resolve and the reject, okay? So this particular promise is going to be responsible to handle is when the response exists, okay? In this case, when the so exactly when response it is, okay? And in this case, because it's going to return now an object, and I want to return out a function, they're going to take is some of these arguments, right? Particularly in this case is just like this. This is promise object that is going to keep track of that. I want now is to, well, call the function, callback function here that I'm going to pass here, right? So this new promise reject or this, okay, that's when we need to actually clarify our ideas here a lot, right? Because it's this resolver outer and the reject, right? So when that happened, because after all that's what represents this, okay? So when that happened, I want you to now is run a callback, right? So in this case is that say, hey, when there is a response, okay, when there is a response, I want to call it with this, say, hey, response. You can create now a function around this as a way to easily test this, which is now promise one, say promise one, right? Where, oh my god, what's wrong with me? Counts here as promise. You can say, hey, this will be now a function that is going to return is that, right? You say, hey, this is great. This is great because this is what I want to return, right? I want to return now a new promise with that, but I want to now pass is this, I want to execute is the callback that you're passing to me, right? So far so good. Invalid arrow function. Parenthesis the wrong and arrow function. Okay. I get it. I get it. Is this one, right? Is this one? Is this one? Is this one? So as a way to actually improve the readability, here we can say something like this. Hey, I want you to now run. So this is a function that inside of this is going to return this promise, okay? That inside of this promise object will call as the response with that particular callback that I'm passing, right? Invalid arrow function. Missing formal parameter. Missing formal parameter. Missing formal parameter. What is it? Syntax error. Okay. Missing formal parameter. Respected number 3. Formal parameter is a fancy way to say function parameter. Yeah, but it's missing formal parameters. Well, is this one. Invalid error function. Missing formal parameters. But I want to return is this, right? You know what I mean? It's like I just want to return that. Missing formal parameters. It's because I think you are assuming is this one. Which is you are now returning as a new promise object that inside of this is going to call is that. Okay. Exactly. I'm passing out a new promise. Okay. Okay. Oh my god. Okay. Is this? Wait. Yeah, it makes sense. It makes sense. It is this. My bad. You know, there are readability problems here. This is readable problems here. Makes sense. This is readable problems here. You know what it means? I have this kind of error, but it's because it's my way of how I interpret this. Okay, but this is the way how you can write a function. Makes sense. So with that, all right. Now that I create this, is like okay. So this promise, I'm gonna create now another function, which will be is the callback here. You know, a callback call here, a function that it say hey, it's gonna get some data. All right, and I want to now return or console log only do this instruction, which is a callback followed by the data, right? So what happened here is that when we're writing our promise and assigning this particular callback, once the promise is resolved, okay, because that's what it's doing is assigning this callback here. Because here we need to okay, that's right. Because here we're doing is this one, we're gonna pass this callback data, and this callback it say hey, passing some data, you know, so passing data, right? Or the hello world, you know, hello world, and here is this. So what happened here is that not only that you're calling is this promise, where you're passing is this callback, and you may say, what is this callback? Hey, this callback is this function that is going to only return this. Okay, so I'm calling this callback is to what? Is to promise. But what is promise? Is now this function that now it takes to that now it returns a promise, okay, that I'm capable is to run that callback that I pass based on that. So actually let me clean this, okay, and let me actually put all of this as it is, right, followed by the callback here, what is a callback here? Exactly, follow the callback. And when you want to make use of this, you know, you need to actually is to go forward, to go after other lines of code, to go through other line of code. So it's not written in sequential. It's not written sequentially. So promise one, and this is not the callback that I'm passing to this, that accepting that to actually get triggered when that happened. In other words, is say, hey, I want not to trigger is this promise dot resolve, okay, and passing this callback, this function. So the thing here is that you will need to actually go into another line, go into other stuff here. Going into another line, to another stuff here. This inversion control things. Okay. But in any case, we slowly gain a little bit context of this Thunk thing here.
Cool. All right, let's talk about a pattern on top of callbacks. This has actually been around for a really, really long time. It way predates JavaScript. This terminology didn't even really exist in JavaScript until people started trying to adapt this notion in JavaScript, and the word is Thunk. I have no idea where they came up with this word. I don't know what they were smoking. I wish I had some of it. It's
I don't know what they're smoking when they...
It's a weird word. I don't even know what its origin is. But I can describe to you what a thunk is. And it's actually kind of deceptively simple what a thunk is. From a synchronous perspective, a thunk is a function that has everything already that it needs to do to give you some value back. You do not need to pass any arguments in. You simply call it, and it will give you a value back. Does that sound familiar? Everything already, that kind of deceptively simple what a thunk is. From a synchronous perspective,
it is important. Okay. Exactly. So, exactly. So thunks. Thunks. Okay. So, exactly. So what is a thunk? That's a very good question. Okay, and slowly but progressively we're starting to explore that. What's a thunk? From a synchronous perspective, is a function that when we call it, it gave us what we need.
A thunk is a function that has everything already that it needs to do.
So if, for instance, synchronous perspective is a function that has everything it needs for the function point of view
to give what a thunk is. From a synchronous perspective, a thunk is a function that has everything already that it needs to do.
Exactly. It's a function that has everything it needs, that has function. It's a function that has everything it needs
to give what a thunk is. From a synchronous perspective, a thunk is a function that has everything already that it needs to do to give you some value back.
So it's a function that has everything it needs to run.
Do not need. From a synchronous perspective, a thunk is a function that has everything already that it needs to do.
It's a function that has everything already. It's a function that has everything already it needs to produce the outcome.
To give you some value back. You do not.
To give you some value back. You don't need to pass.
Not need to pass any arguments in. You simply call it.
You just don't need to pass arguments to that. you just simply call it, and you're gonna get,
and it will give you a value back. Does that?
You simply call it, and it will give you a value back.
That sound familiar? You remember how we were talking about that before in a different workshop? So a thunk is just a function with some closured state keeping track of some value or values, and it gives you those things in a different workshop. So a thunk is just a function with some closured state keeping track of some value or values, and it gives you those things back whenever you call the function. Here's a synchronous thunk. I've got a closured state keeping track of some value. You remember how we were talking about that before in a different workshop? So a thunk is just a function with some closured state keeping track of some.
So a thunk is just a function with some closure state keep track of
value. You remember how we were talking about that before in a different workshop? So a thunk is just a function with some closured state keeping track.
Exactly, with some closure state to keep track
of some value or values, and it gives you those things back whenever you call the function.
A thunk is just a function with some closure state that give it back to a function that run that function with those arguments.
A thunk is just a function with some closured state keeping track of some value.
Exactly, with some closure state keeping track of those values and passing back.
Or values, and it gives you those things back whenever you call the function.
And give you the values when you call that function. But this is from the synchronous perspective. So from the synchronous perspective, it's just a function that has everything already it needs to give. It has everything that it needs to give you some value back. So you just don't need to pass arguments to that.
It's a synchronous thunk. I've got an add function which expects an x and a y, and I make a thunk that calls the add function and already has the 10 and the 15 in it. It's hard coded in this case. So every time I call, like I do on so that's line 6 to call the add function, but every time I call line 9, if I call thunk over and over and over again, I'm going to get the same value out every single time. So now, here's the important part. Thunk itself, that value which is a function, it has become a container around that particular collection of state. And that is now a container.
So this thunk now is a container of a particular, this thunk is now a container of a particular state
that I can pass around anywhere in my program, as it has become a container around that particular collection of state.
So this thunk now is a container of a particular state or state that I can share across my entire program. Oh my God, here we go. I'm telling you.
And that is now a container that I can pass around anywhere in my program as a container wrapped around that state. And anytime I want to extract it, I simply have to call that function and I get the value out. I don't have to pass the value or the state itself. I pass the wrapper around that state all around my program. So it becomes like a token that represents this value, and it's easy to get it out. All I have to do is execute.
So this thunks represents a token that is easy to pass around my program and get and call it whenever I need to get that value.
executed to get the value out. You may not realize it yet, but that is the fundamental conceptual underpinning for what a promise is. A wrapper around a value. Here, the wrapper is a function. In promises, it's a much more sophisticated thing. But it's actually quite powerful to think about when we extend thunks from this synchronous nature into an asynchronous nature. This is a synchronous thunk, and that's the most common definition for thunks you'll find, is that it's a synchronous thing. What is an asynchronous thunk? Well, there's no right or wrong definition here, but the most natural way that we could define an asynchronous thunk is that it is a function that doesn't need any arguments passed to it to do its job, except you need to pass it a callback so that you can get the value out. So that's what we're going to call an asynchronous thunk. So let's extend our synchronous. You need to that we could define an asynchronous thunk is that it is a function that doesn't need any arguments passed to it to do its job, except you need to pass it a callback so that you can get the value out.
So from the asynchronous perspective, from the async POV, okay, so from async POV is this. From sync POV is this. Oh crap. grab. So from the async POV,
function that doesn't need any arguments passed.
So it's a function that doesn't need any argument passed except for the callback when you
to it to do its job, except you need to pass it a callback so that you can get the value out.
Exactly. Except you need to pass a callback to get the value the value back.
Is that it is a function that doesn't need any arguments passed to it to do its job, except you need to pass it a callback so that you can get the value out.
Except you need to pass a callback to get the value back.
Except you need to pass it a callback so that you can get the value out. You need to pass it a callback so that you can get the value out.
So you can get the value out. So exactly. A callback so you can get the value off. And this subtle distinction here is very
That's what we're going to call an
important.
asynchronous thunk. So let's extend our synchronous thunk to an asynchronous thunk. I have an add async function.
In this async thunk, right, where in this is actually now calling a function that is actually performing these async operations, all right? And the only thing that we want to do is, and the only thing that we want to pass is now a callback to do its jobs. We want to pass the callback to get the value out of. Dim sum.
It fakes some asynchronicity with a set timeout. Takes the callback that you've passed in on line 1. On line 3, it calls it with the addition. So we make our thunk on line 7 with add async, and we hard code 10, 15 in CB. And on line 11, we have that value, that thunk value, that we can pass around our function. And every time we call thunk and pass in a callback, we know we're going to get our value out. But here's what's incredibly powerful about this pattern. From the outside world, we do not know, nor do we have to care, whether that value is available immediately or whether it's going to take a while to get us that value. What difference does it make to us? We pass in a callback. We know you'll call the callback when you have a value ready for us. So the first time we call thunk and we pass in a callback, it might have to do some significant work to calculate the answer to our question. It might make some AJAX call and do some other kind of crazy calculations, and it might take a while. And then it may decide to memorize the answer to that question so that the next time you call it, it just gives you the value back right away. But from the outside world, does it matter to us whatsoever how that works? What's happening here is that by wrapping this function around the state and allowing it to be asynchronous in nature,
by wrapping a function around the state,
we have essentially normalized time out of the equation. We have factored time out of the equation. We have produced a wrapper around the value that has become time independent.
We have produced is a value. We have produced is a wrapper. We have produced is a wrapper. We have produced is a time independent wrapper around a value. We have produced a time independent wrapper around a value by holding the state, and whenever it is ready, get the value out of it. Get the value off it. Get the value off. Exactly, get the value off.
It doesn't matter if the value is there now or if it's going to come later, we still use it in exactly the same way. Hear this, if you don't hear anything else that I've said today. Time is the most complex factor of state in your program.
Time is the most complex factor in my program or in the life. It's the most complex factor state in your program.
In your program. Managing time is the most complex state in your program. That's why this is huge, to be able to come up with a very simple, there's no libraries involved, this is straight up core JavaScript, just a different way of looking at and using the mechanisms that have been available to us for all 20 years. We've taken this notion, this fundamentally difficult thing to reason about called time, and we've eliminated it as a confusing factor, as a complicating factor. I have this thunk, it represents a value, I pass it around whenever I want the value.
Exactly, I have this thunk, I have this state that is a container of the states, that it represents the eventual completion of the value.
I give it a callback and I get the value out, and that's all I have to do.
And I give it a callback?
I can tell from your faces that you're not realizing how groundbreaking that notion is, okay? But that is one of the most important observations. I couldn't believe, when I recognized what that meant, I could not believe how far I had gotten in JavaScript without that realization. It changed everything for me. And in fact, it's what helped me understand promises. Mm-hmm. I didn't fully understand the conceptual basis for promises until I understood what thunks were doing. Because we'll find out that a promise is a time-independent wrapper around a value. It just has a fancier API.
Promise is a time-independent wrapper around a value.
So as I said earlier, I like to say that thunks are promises without the fancy API. Okay? Now, there are some twists, there are some wrinkles that we can throw into the situation. If I wanted to make a thunk, give myself a generalized utility for making thunks, I can do all that old crappy array stuff and pushing the arguments on and calling apply. I could do it that way. And I could use it this way, as we see on line 7. So now I'm not manually making one, but I can make any thunk that I want by presetting the callback as the first argument, and anything else that I pass, it's going to get passed along to it always. And that's how I could produce my thunk. So I could make myself a utility for making these, which would be not fundamentally terribly different from a promise constructor. Make thunk would be kind of like a promise constructor. It's a constructor for thunks. Yes?
Could you go through the, so when we talked about the problems of callbacks, this inversion of control, not too early, not too late, not too many times, and just expound a little bit on that with how the promise thunk is.
We're actually not gonna have any solution to inversion of control with thunks.
Yeah, okay.
Promises are going to solve inversion of control.
Okay.
We're not quite there.
Yeah, okay, that makes me more...
Yeah, we haven't solved inversion of control yet. We're laying the conceptual underpinning for promises, and that's why we're looking at that.
Yeah, I just wanted to, because that realization happened earlier, when we were like, now getting a better understanding of what promises are.
Yep.
And just wasn't sure how much the fancy API is, solving our problems, or how much is the thunk solving.
Yeah, got it. The thunks really aren't addressing inversion of control. The nature of how promises are designed to solve that. So we'll get there. Okay. There's a question about going over slide 39 again. This is a synchronous thunk. As you can see, I have an add function that receives an x and a y, and I make another function.
Thunk is this function that have everything that it needs. Okay, so a thunk is a function that has everything that it needs to. No, but this is an asynchronous. From the synchronous perspective, a thunk is a function that has everything that it needs. So when I call that, so it's a function that has everything. It's a function that have everything already it needs to get a value something, to get a value back. So you don't need to pass any argument to that. So just simply call it and give it the value back. Okay? So a function behind the scenes is now a closure and keeping the state exactly. A function, a thunk is just a function with closure state keeping the state. So a thunk is a function. A thunk is a function with some closure. Okay, so a thunk is a function with some closure. Here you're not creating a closure. This is when you're creating a closure. Okay, so a thunk is a function with some closure to keep track the state of those and give you the values when you call that function. And this is something important because it's a keep track is the state using closures, and that make it portable, which means that with this function, that anytime we call them, it already have all the argument that it needs to. So we only get is the value out of this, which makes this portable, so you can use across all of your program. When we look now this from the async perspective, which is now a function that you don't need to pass any arguments to it, just the callback whenever that is done, so you can get the value out of that asynchronous. So we produce now a time-dependent wrapper around a value, and time is the most complex things to manage in your program. And this is something, time is tied to the and time is something that is tied to the async operations, side effect operations, anything that happens outside of the normal flow of the execution. In other words, is a network request, user input, computer inputs. So interesting. So this now lays the foundation of the promise of how you can have this time wrapper in a time-dependent wrapper around a value with some fancy API. Holy crap! And this is only using is the tool that already exists in JavaScript, which is now a closure that's going to keep track of the state with some closure. It's going to keep track of the state, and therefore you can get the value out of this whenever you want by only just calling that function and passing that a callback. Interesting. Okay. Holy moly. That'll be all for this video. Take care. Bye bye.